It seems it works. Yeah, because there was a red light, now it's distinguished. Okay. Therefore, let me remind you that we are about, it's section 3, infinite dimensional spectral theory. And the first thing that I would like to, in fact, I presented examples of Hilbert spaces. And I gave two examples. The first one is a L2Z, just to be short, double infinite sequences of square summable, yeah. And the second was a space L2 capital on a certain interval I. You can think about the interval AB, just a, and these are just now functions of continuous variable such that the integral is we are going to use mostly three cases: L2 0 1, L2 0 infinity, L2 on the whole axis, most important for us. And now let me give you a few examples of infinite dimensional operators just to see new phenomena completely absent in the finite dimension case. And the first one is the operator which I denote n hat, which is defined, which acts you always have to start from the space, indicating the space in L2Z in very simple fashion. Just multiplication by your vector is just a double infinite sequence. You multiply the member of the sequence number x by its number x, yeah? And you see immediately that this operator, not usual one, there is a property which is absent in finite dimensional case. It is not defined on any psi with this property, because not any psi such that the squares are summable, these things not necessarily summable. That means that you can apply your operator. You are not allowed to apply your operator any element of your space. The result of application could not belong to the space. So this operator has a lot of, in fact, okay, at least three. Let me mention three negative properties of this operator. Not everywhere defined, everywhere in the space, yeah? Not continuous, despite that it is evidently linear, because you can take a function like that and then just cut it after. You can take any L2 function and just consider the sequence of vectors in which all components except minus n, between minus n and n, are zeros. Yeah? They are evidently convergent to this vector, but the result of application is not. Therefore, it is not continuous. And third property, unbounded, which somehow sums up the two. Unbounded. This is in fact the term. That means that your operator, in fact, it is proven in general theory that these two properties are equivalent in that. Yeah. And the second, let me consider the, as simple as before, I take now the operator x hat, which acts in L2 0 1, again, the same fashion, like multiplication, but now it is multiplication by continuous variable. So it is everywhere defined, because if you have a function which is square integrable on the interval 0, 1, after multiplication by x, nothing bad will happen. It will be still square integrable. But now I'll try to find eigenfunctions and eigenvectors of this operator. Yeah, I have to write the corresponding equation. X psi equal lambda psi. I am looking for the solution of this equation. And now let's write in the components. We know how does operator act, and it will be x psi x is lambda psi x. And the corresponding function should be 0 for all x except lambda, and this function is 0 with respect to the back theory. In the back integration theory, function which is 0 everywhere except a point in which it is 1 or, okay, it is nothing, yeah? And the only possibility to have something reasonable from the point of view of common sense, non-trivial, you have to assume that the corresponding eigenfunctions is just delta function, yeah? But delta function is not L2. Therefore, we have two phenomena. First, it is not necessary, you are not allowed in general to apply your operator to any vector in your space. And the second, you see that you have to modify the notion of the spectrum, because if you would like to solve a spectrum problem, you have you can come to eigenfunctions that they are not in the space. Delta function is, okay, in fact, it was introduced by Dirac in 30s precisely in this context. It is not usual function, it is distributions. You have to apply certain efforts to make a reasonable definition. And maybe the third example, which I denote by hat, p hat, it is just operator which acts in L2 on the whole axis, and it is very simple. Just again, I can give you a family, infinite family of eigenfunctions. I just write psi lambda is E lambda x. You can you can easily verify. I put minus here that p psi lambda is lambda. So we have now the solution is not generalized function, just very nice function exponent, but it is not square integrable on the whole axis, because its absolute value 1, and integral over whole axis of 1 is infinity. So a similar phenomena. Your eigenfunctions being very nice functions, there is no better functions in analysis than exponent. And nevertheless, it doesn't belong to your space. Something wrong is going on. Okay, what is the conclusion? Conclusion that I think we are encountered with two new phenomena absent in finite dimensional case. First, you are not in general. You can't apply your operator to any element of your space. And second, you have to modify the notion of the eigenvalues in eigenfunctions, because if you use the standard notion, which you extract from finite dimensional theory, you'll encounter certain problems. Your eigenfunctions could not necessarily belong to the space. And therefore, we have to be careful with these things. In particular, so this operator, third one, has two properties of the previous two, because, its eigenfunctions do not belong to the space, and it is unbounded, because if you take it off, you can easily find L2 function whose derivative, is not square integral. Yeah? And now, these two examples shows us that we have to introduce something which is known as a domain. I will not discuss too much this point, but just domain of definition of A denoted D on A, standard notations, not necessarily is the space. It could be less, like in this case, like in any of these cases, yeah? And second, okay, these are conclusions. Modify the notion of spectrum eigenvalues and eigenfunctions. Okay, now the definition that works in infinite dimensional case, and it is widely accepted, in fact everywhere accepted. Okay, let me give you this. But first, okay, let me say that, as I said, there are two phenomena, at least here. First is that your operator is not necessarily applicable to any vector in your space. And second, okay, your eigenfunctions could be a bit bizarre. So the first phenomenon, which is known as unbounded operator, is quite tricky. There are big books that discuss nothing as that, but I will not discuss almost completely, because it turns out that it's not so important for random Schrödinger. Somehow, random potential is, roughly speaking, almost always bounded, and for that case, there is no problem. I'll mention a bit later why I will not be too serious about the first phenomenon. I will be mostly serious about the second phenomenon. That you have to be careful with the good definition of the spectrum, and you'll see that there are very interesting types on spectrum that are absent in the finite dimensional case, and which are just standard, that common precisely for random Schrödinger. They were not before. In classical spectral theory, these types of spectrum were a kind of just possible, but not really existing. Okay. So let me just self-adjoint. I'll give you several notions that I'll not discuss too much, just to finish with the first point. Self-adjoint operators. The notation will be SA. Yeah? I have to start from the definition of adjoint, like before. So what I do, I take a vector from the domain of definition. I am given an operator. Since these words include that I know the domain of definition, I know to which vectors I am allowed to apply my A. Yeah? I have an element from the domain of definition. I apply operator. Now I make a scalar product, and I write it in that form. And the operator that allows you to compute this thing by using something in the second argument is called adjoint operator. And it is easy to see immediately that the domain of this operator in general could be bigger than the domain of that operator. Why? Because if y belongs also to just like that. I will not, better not to ask me questions, because it will lead us very, very far from the subject of my course first, and I'll be completely out of the time. Yes?
Did you mention, maybe I missed it, that A is symmetric?
Huh?
A is symmetric, right?
No, I didn't mention. No, I didn't mention this. No, I didn't mention this. Is just adjoint operator. No, you get the same result acting on the second factor. This will be the next. Yes.
Operators
Sorry.
For which adjoint is defined in the less than network.
One more.
No. Then this is simply D oasis star will not contain.
Sorry.
In general.
Okay. Let's finish. Yes. Now I am going to define symmetric operator. You can do it in inverse order. Symmetric operator is the operator that satisfy this condition. For example, if you take for the operator n hat all functions, all sequences with finite number of non-zero members, it's good domain of definition. Why not? It's myself who make the domain of definition, and you can easily check for if you have vectors with only finite number of non-zero components, your operator n hat will satisfy this property, evidently.
X and Y.
Huh?
X and Y in addition.
Yeah. Oh, excuse me, please. Yeah. The both, unlike here. Here, in that equality, only first argument is required to belong to the domain. Yeah, and now you can define the self-adjoint operator. It will be defined like that, just operator for which the definition is the same, but only now the quality is the same as in finite dimensional case, but the objects here are defined in much more complicated way. And to understand that, so I repeat, I do not want to discuss too much this point, because we will not be serious about that point in what follows, but I just would like to show you a simple example. It will be simultaneously an exercise to showing that it is not just imagination of mathematicians that would like to put all the dots in proper places. This is all. And just an example. Take the operator in L2, 0, 1. Yes. Domain of this operator. Okay, let me write. It will be my A, yes? Domain of A is C1. So continuous differentiable functions such that zeros, they are both zeros at the endpoints of the interval. So continuous differential functions that are 0 at the 0 and 1. And you can easily check that the operator is symmetric, just integration by part. It is simple integration by part exercise. But now I would like to say that the domain, now the operator A hat is again d over dx formally, but the domain of definition is just C1, at least more, but it is already without no condition here. Because all the same, you have to integrate by parts. And that the operators, that there is a gap between this and that, you can check easily just by showing that the function psi on x equal e z on x. Z is a complex number. So this function, okay, it is the eigenfunction of this operator, a star. But of course, it is not the eigenfunction of this operator, because if it would belong to the dA, you can easily prove that Z should be real. Everybody knows how to prove that if operator is symmetric, the eigenvalues are real. So I repeat, this function is a satisfy the equation and for any. So if I take a Z real complex, I know indeed complex, genuine complex with imaginary part not zero, nevertheless, of course, this function solves the equation, and so it is a kind of eigenfunction, but it couldn't be if this operator would be self-adjoint. Therefore, this is a reasonable precisions that I repeat we will not discuss too much. And now I would like to pass to the definition of the spectrum. The spectrum of self-adjoint operator. You know, when people in spectral theory say spectrum, you'll see just in 10 minutes that there is a certain ambiguity, because first when people use to speak about the spectrum, this is just a set of real numbers that solves the corresponding equation. But in fact, there is more which we are going to learn quite soon. But first, of course, the definition. I define first a certain set, which is called resolvent set. Yes, this is of my operator A. The resolvent set is a set of complex numbers, of numbers, complex plane, such that is, has the bounded inversion. This is a definition. So I repeat, I consider the set of all numbers of the complex plane, maybe real, maybe not, such that the operator A minus Z is invertible. Not just, but as a bounded operator, because we already learned that there are operators that could be unbounded. But I require that the inverse was bounded operator, with the bounded operator. So this is so-called resolvent set. And then the spectrum.
Sorry. Something trivial again. You didn't say what bounded means. Probably it's obvious to everybody.
It's just make negation of all these things that I wrote here, because it's unbounded. So you can apply, no, in fact, bounded, that means that it doesn't matter to which vector you apply, you obtain something which is again a vector, your space. Yes. Okay, and now the spectrum.
Inversion.
The spectrum, which called sigma A, it is just, it's very simple looking thing. Just the complement. And this set is obviously open, because if your operator is bounded invertible, you can just shift a bit Z, it will be still bounded invertible. Therefore, the set, resolvent set, is always open, and its complement, of course, is always closed. Yes? Again, excuse me, but I have no time to explain what does it mean, open set or closed set, but it will be important to have this in mind. So, unfortunately, I have to say that the rate of the accumulation of notions and complexity is much higher than, but there is no choice. Yeah. Okay. And so this is general definition, which is applicable not necessarily for self-adjoint operators, but if it is if A is self-adjoint, then the spectrum is always real, which is, by the way, good, because we have found at last something that is similar to things that we know from the finite dimensional theory, because we know that eigenvalues of Hermitian operator in finite dimensional space is always real, are real. Yeah, we have the same property, and to prove this, you have to just compute very simple thing, which is even less than exercise. You take a vector psi, of course, belonging to the domain. You assume that your operator is self-adjoint, yeah? What does it mean, self-adjoint? That you have this property, yeah? And you can, if you compute the square of the norm of the self-adjoint operator, abstract one, you will find now that, oh, excuse me, I made a mistake. A minus Z, because I would like to compute something about the invertibility, yeah, of this operator. Because if I'll find on which set it is invertible, I'll take a complement and it will be the spectrum. Now I take a number. I take any complex number. I compute this norm. Yeah, and the result, I repeat, easy exercise will be exercise. I repeat, you use nothing except the possibility to play with the place in which you put your operator. And you see that if imaginary part is not zero, doesn't matter what is going zero. You have a bound. So your operator, if the operator is self-adjoint, it is always invertible for non-real z's. The A minus Z is always invertible if you put there non-real number. That means that resolvent set, or you can, rho A is at least all non-real numbers.
Using the fact that if you have a bound from below, and you have for the inverse, you have a bound above.
This I will tell at the moment, but if you see that so on any vector, your operator is bounded from below by a certain thing, that operator is invertible. Otherwise, yeah? And now, so this is the definition of the spectrum. So what I did, I defined the spectrum via resolvent set, and I showed that if operator is self-adjoint, then its spectrum is always a subset of real axes. And just to finish, because we almost found a very important and useful object which will appear many times in lectures by Spencer and I believe in Holtscheid, that there is a very important operator which called resolvent of my operator A, and notation will be G A on Z, which is just this inverse. And we know for sure that at least in this case it is bounded. It exists in bounded. It could even exist for certain real z's, but it's already another story. It depends on the A. But this we have for any self-adjoint operator. Yeah? Resolvent is well defined, means bounded operator for all non-real values of this so-called spectral parameter. Okay. And by using this definition, you can easily find that the spectrum of the operator n hat, which is here, is just Z, and the spectrum of the operator x hat and both spectrums are impossible in finite dimensional case. First case, because it is infinite set. And second, because it's continuous set, all numbers from 0, 1. In both cases, your spectrum is infinite, yeah? Okay. Let me. And by using this bound, yeah, you can easily find that the norm of the resolvent, in fact, it's just another form to write. And this bound also will be used many times. It is just nothing that this line. Yes, and to finish, I need one more thing, which is called resolvent identity, to finish with resolvent. It is just simple algebra. If you have two operators, A1, A2 are self-adjoint, then you have a formula which is extremely useful, despite that it is extremely simple. Okay. I repeat, just simple algebra. and it is valid, of course, for all non-real z. Okay, now we come again to what is a spectral theory in infinite dimensional case. We see that we have to modify notion of the spectrum and in fact the very notion of the operator, because now we have to think about the domain of definition. And now the spectral theorem, but I specially, in the first lecture, I gave specially that form of the spectral theorem in finite dimensional case. There are many forms, at least three. I gave two, and Jan Fedorov gave third, because it is the most natural from the point of linear algebra that any self-adjoint operator possesses a basis in which it is diagonal. But this form is not too good for infinite dimensional case. This is why I didn't mention this. But now the spectral theorem. For that, I have to first introduce a certain very interesting thing, which is called resolution of identity. What is it? It is a function which will denote by script the function, okay, that, it's hard to say how to, okay. I write by words. It's an orthogonal projection valued function of intervals of real axis. So given an interval, you have a projection. For any interval of real axis, you have a projection. This is a function that I define. That means that we have to write like that. I have a interval delta, and for every delta, I can present an orthogonal projection, which has two properties. First one, if I have two sets, delta 1, delta 2, of real axis, then, and I take the product of these two projections, it will be the projection on the intersection. And the second property, if I have a sequence of intervals pairwise disjoint, delta G1, delta G2 is empty set for all pairs G1 and G2. So I have a sequence of intervals that do not intersect. Then there should be property. I require the property which is called sigma additivity. So it's not simple story, this function by definition, but in fact it is a simple thing. You'll see now. So once more, if you'd like to say in compact way, so what is the resolution of identity? This is a sigma additive measure, but what is measure usually? For any interval, you have a positive number, not negative number. Here, my measure has values not non-negative numbers, but orthogonal projections. So in a way, this is people used to say this, it's orthogonal projection valued sigma additive measure. And don't be too cross, because just recall at the moment, classical finite dimensional spectral theorem. You may remember that I wrote, okay, this is 0 if L is different to M. If L is equivalent, it is just 1, yeah? But it is just this property if two sets do not intersect. And there was another, now in fact, if I have this system of, you may remember that I said that the system of projection of this kind is called complete. Now you can define the measure here the measure is defined like that. So I introduce new notion, but just would like to show you that if you take classical finite dimensional spectral theorem, and if you define the measure like that, just you take an interval. You remember we had the projections, and we had the real numbers, which are eigenvalues, yeah, lambda L. So you just take delta, compute how many lambdas in this delta, and put corresponding projection. You can easily verify that these properties are the case. Okay. But in general, you see, I do not require that the measure is as simple as that. Any measure of this kind, this sigma additive orthogonal projection measure will do. And by using this notion, I can now write, and this is now it's for every self-adjoint operator A, there exists, and I will not precise what in each sense, and essentially unique. It's not important at the moment. Unique resolution of identity EA such that okay, I repeat. No, here I assume that you are familiar not only with the notion of the Lebesgue integral, but the notion of the Lebesgue-Stieltjes integral. But I have no choice I have no time to explain. Just I would like to say, if your measure like that, it consists, as mathematicians used to say, only from atoms. There are only atoms, discrete points, just sum of delta function, yeah? Because I can write this projection one more. E delta is just a sum. If it is indicator, chi delta is indicator of interval delta. It is 1 if argument in delta, 0 outside. Therefore, the measure written over there is here. But in general, it could be, we are going to see that measure could be quite bizarre. But this is a spectral theorem which says, in fact, the same. But in fact, it says more, that dA, what is a dA? It turns out that dA is a set of vectors such that, excuse me. So it might be a bit strange notation, but you see, if you have operator valued measure, after multiplicating by after constructing this scalar product, you have standard measure. It's easy to check with just standard measure on the line, whose values are non-negative numbers. Therefore, I am dealing here with the standard Stieltjes-Lebesgue integral. The only difference that I am in spectral theorem says that I can do this for any psi from the domain of definition. Moreover, it says that the domain, the definition itself, is given by this equality. So the statement is that given a resolution of identity with that property, you can easily construct an operator. But the contents of the theorem, that the converse is also true. Given an operator, there is a measure in essentially unique that provides you with this very useful representation, which is in fact nothing as an infinite dimensional version of the spectral theorem for self-adjoint operators, which I am going to use quite heavily right now. Yes?
To write the completeness conditions explicitly?
It's very good point. Excuse me, please. This, in fact, I forgot. Thanks a lot. So if you take the measure on the whole line, the value of the measure whole line is just operator, unit operator. Yeah, thank you very much. Okay. This abstract definition leads, maybe to finish, I have to write two more formulas. Now assume, quite useful, that we have a function of real variable but with complex values. Yeah, I would like to construct a function of my operator, a square, a cube, exponent of a, etc., etc. What do we do in finite dimensional case? In that case, GI is very simple to define. Finite dimension, you write GA is G lambda L PL. This is all. This is the definition of a function in finite dimensional case. You can easily check that this definition is compatible because we have an independent way to define, for example, a square. Just multiply twice a. You can easily check that this definition, trivial definition, is compatible with mine. But since we reformulated in this way the definition of a function of your operator, and you have an analog of the formula that we have there, that you can write easily G on A is integral G on lambda, and the same measure
Oh, there's psi on the right, but not on the left.
So, excuse me? What is the question?
You're taking the expectation of the operator on the left.
Ah, yeah, oh, excuse me. Okay. So I write everywhere psi, but in fact, there is a more strong definition which I do not need. In fact, you can write stronger form, which it's called weak form. There is a stronger form in which instead of doing scalar products, you just apply this formula to a certain vector. But this needs certain notions that I don't want to introduce. For me, it's more than sufficient. Now, doing that, having that, we can pass to one more thing, which, by the way, is very useful. Okay, we have a notion of the self-adjoint operator. As a byproduct, we have a notion of the resolvent that I said is useful. And we have a notion, we have now the assertion, this is spectral theorem. In particular, I just would like to use this general definition to write the resolvent, integral representation for the resolvent of my operator. What is it? Okay, from the general formula, we understand that it will be like Z. Because a particular case of the function, what is G by its definition? There is, you see, it is just simple function of the operator. And I replaced A by lambda here, but the price is to write this integral. Yeah, and this formula is useful because it allows us to, you see, the problem to find the resolution of identity given an operator is in fact the reformulation of this direct problem of spectral analysis. This is the same as to find all eigenvalues in all eigenvectors. So the problem is not simple, of course. But assume that we know the resolvent. Just, okay, the God told us when we are sleeping that resolvent is that and that. That in that case, you can find, unfortunately, I have no time to explain, but there is a very nice formula expressing the resolution of identity via resolvent. It's called, it's called, okay, there are many TTS-Perron formula. Yes?
Do you assume that the endpoints of the interval are not in the system?
Okay, this is too fine question for me. You know, too precise. Yeah, in fact, there are subtleties that I have no time to discuss. You can define everywhere in this point, you can half sum and you are done. Yes?
Another question, is there any reason that you define this function epsilon only on the intervals and not just as a function from some dense set to operators?
Not, but you see, the function, this is a, you mean resolution of identity?
Yeah.
Yeah, but resolution of identity are projectors. Norm of the projector is 1. And if you have a operator, bounded operator, define it on any dense set, it is defined everywhere. Therefore, it's more or less the same. Okay, and now let me pass. So it is just useful formula if you know by chance the resolvent of your operator, which is in classical mathematical physics is called Green's function. And there will be a lot of this notion in the Tom Spencer lectures. Therefore, you can find the resolution of identity. It's a very useful and efficient tool to work with in spectral analysis. Yeah. But now, my next point maybe most important in that section is called spectral types. And the first item to mention, let's recall the classical Lebesgue theorem, that if you have any non-negative finite measure can be decomposed as follows. So we have measure mu. Now it's not operator value, just a standard measure. What does it mean? So you have a sigma additive function with no negative values defined on the intervals of the real axis. We call it mu, and the measure mu could be written always as a sum of 3 parts, which are denoted AC, SC, and PP. And this is a mu SC is absolutely continuous part of mu. Okay, in physicist world, this is simple thing. Just if you have there is a function rho such that you can write this measure as an integral of this function. A function, of course, called density of the measure. Yes?
Yes, this formula is no.
Sorry?
Is there some imaginary part missing?
Certainly, yeah. Oh, very good. Yeah. Okay. There is a second part which is also easy to understand. The third one, in fact, here. I just write because it's the standard way to write. Everybody writes like that because despite that the middle term is harder to understand. Okay, MPP is some simple thing, just the atoms of the measure. So what is it? It is a collection of real numbers such that if you take, this is again standard notation for physicists to know, if I write lambda with this curly brackets, that means that the set consisting of only this number. So the measure of a given point is not 0. It's called atom of the measure. So it is not strictly positive.
So it consists of...
So if you have, it's easy to understand that if you have points of the measure, there should be not more than countable number, because otherwise your measure will not be finite. Yeah, I wrote finite measure. What does it mean finite? The measure of the whole line is finite number, yeah? So there is no more than countable number of points, atoms, and this is a pure point measure. But be careful. This point could be dense. For example, the set of points which are here could be just all rational numbers. And it is precisely what happens in localization theory. So be careful. Don't think about these countable points just like Z or something. Is that they not necessarily isolated. And since the spectrum is point set, too complicated.
Is there an example of a dense point spectrum?
Standard spectrum in the Anderson localization is point. Shmuel.
Another problem.
Yes.
Another example. Is there another example? I know that example. Is there another example?
You know, you would like the answer about another example. There is inverse problem of spectral analysis that says that you give me any measure, whatever you want, any pure point, continuous, and I give you the operator, Schrödinger operators, whose spectral measure is measures that you gave me. No. But the point is, it's very hard to find which potential is. But you would like to say that you know which potential produces this measure.
No, I'm asking, is there an example that is rigorously known that produces such a potential and it is not of the standard Anderson types?
I said it exists, but it is very hard to say which one.
Okay, okay.
No, you asked me, is there exist? Yes.
Yeah,
Existence, yes, but what are properties? Come on. No, but they're almost periodic functions. There is a lot. You would like me an example, please?
Yes, okay. Okay. The almost periodic functions, yes. Yes, okay.
Discrete Schrödinger Maryland model. It's special for you. Because you're inventor of this model. So if alpha is Diophantine, you know, yeah? Okay. And the third component, I do not dare to explain what does it mean. Okay. It is something that is not the first and not the third. No, in fact, this was the discovering of Lebesgue. This is Lebesgue who found these things, and he constructed the corresponding measure by using, there is a one-to-one correspondence between measures and non-decreasing functions. Assume that I have if you have a function fx1, fx2, non-decreasing function, yeah? Then you can always construct this function given a measure. You construct the function in the following way. Just the measure of the semi-infinite interval from minus infinity till x. And if you go to the right, of course, you gain more and more mass of your measure. Your function is not decreasing. Yeah? Therefore, and opposite. If you have a measure, you can always construct this function, and vice versa. If you have a function, you construct the measure for any AB, and that means everywhere you write MAB. I am not about atoms. There was a person who asked me about atoms. It's two. This is a measure. So there is one-to-one correspondence between measures and non-decreasing functions. And Lebesgue constructed the non-decreasing function that define it on the interval 0, 1, that is 0 at 0, 1 at 1. And the derivative is almost everywhere 0. This is what I would like to say. No, it's hard to describe. I don't know how to say. It is very interesting notion, and I would like to say that before random in almost periodic Schrödinger operator, people in spectral theory just used to view this singular component as a nuisance, because the main problem was to prove that it doesn't present in your spectrum. Now we know that it could be present, and it does present, for example, almost periodic operators, etc., etc. And even it is called chaotic spectrum. Okay, but it is just I am reminding you the standard fact from the Lebesgue measure theory. And now having this fact, I can define the spectral types in the following way. And this is a central notion that we will use in what follows. So spectral types now. Okay, I define 3 subspaces. Given I'm again in abstract spectral theory, I have an abstract Hilbert space, and I define this subspace, its collection of vectors of my spaces, such that the measure mu psi d lambda that I define as E so I take only those vectors for which this scalar measure is absolutely continuous. And I take all these vectors. It could be proven that it is linear, that it is a subspace of my space, and much more in fact. And so now it is a standard notation, yeah. And analogously, I define HPP as a set of those H for which mu psi is a pure point. And of course, you understand that I am going to define the third thing in the same way. Singular continuous. This is simple, just definition. But non-trivial points that H alpha, H beta do not intersect. Alpha beta is one of the 3 subindices, and the orthogonal sum of those 3 subspaces is H. In the text that I'm going to give you, I believe tomorrow, there are references in which you can read how to prove and what does it mean more. And now, so these are spectral subspaces. These are spectral. There is no standard name. It's assume that it is my invention, yeah. And now, yes.
Also, is pure point part of the spectrum?
Automatically. Because in infinite dimensional case, subspace, it is closed part of the space. Yeah, and now I define corresponding part of the spectrum of my operator. Yeah, excuse me, I have to put here everywhere A. So I have an operator A. By spectral theorem, there is a resolution of identity. Now I use the resolution of identity to make this decomposition. And now I say that this is definition of the spectrum components. You take your operator. You take your operator. This sign means that you restrict the operator only to this subspace. So you apply your operator A, which is defined, okay, assume that it is bounded, it's defined everywhere, but you apply this operator only to the vectors belonging to the corresponding subspace. And then you obtain, as people used to say in spectral theory, you obtain the contraction of your restriction of your operator from the whole space to a given subspace. It is still self-adjoint, and now its spectrum, it's called, so you define this, and you say that sigma alpha is, okay, let me say, sigma SC is the AC part, component part, or component of a spectrum of A.
You
It's
want to be
called
writing- sorry, sigma on the right hand side, you don't want to write that.
no. Here?
Yeah.
What is wrong? I said that.
Left hand side is being defined, but what's
No, I repeat. See, my sigma is a general definition notation of the spectrum, whole the spectrum. So you take the restriction of this operator and then you take the whole the spectrum of this operator.
Okay.
Okay, and all others like that. Sigma is CA is the singular continuous part, and sigma PP is the pure point part. Be careful, these parts, the spaces, corresponding subspaces do not intersect. But these are just sets on the real line. They could intersect, nothing, in this case, nothing forbidden. Okay, and these are parts of the spectrum, and if we use our examples, you remember we had two standard examples. Now let me give you examples. Better this way. N hat so the spectrum of the operator n hat is pure point. In fact, even more, I'll give you one more classification. On the other hand, we know already that the spectrum is Z. On the other hand, the spectrum of operator I, what is X hat? This is operator of multiplication by the, my God, excuse me. No, nothing bad, except my, yeah. So this is operator on multiplication by independent variables in discrete case, and so n hat, but the operator multiplication operator in continuous case is x hat, yeah. And the spectrum of x hat is purely absolutely continuous, and you remember it is just the interval 0. There is a short example which I give you as exercise. You take, let mu is a non-negative unit measure on 0, 1. Let's take the space L2 on 0, 1. It is standard notation, but now not with respect to the bag measure, but with respect to measure mu. What is it? These are all the functions from 0, 1 with complex values, such that integral from 0 to 1 psi absolute value square, but now I integrate with a measure, and I assume this property. So it's standard measure. You take a book on the back theory and you'll see everything about that measures. The claim is that now I would like to say that the spectrum of this operator, I don't know how to define. No, I didn't define still operator. The operator, okay, it will be x mu. It's again multiplication operator, but now in this special space. And now, depending on the measure in the back theorem, the spectrum will be the same as the type of the measure. So the type of the spectrum type is the measure type. That means, what does the type? Type, that means that which decomposition you have here. So the examples of singular continuous measure are known. In fact, there is a lot. And by using these examples, you can construct here any operator, whatever you want. But it's of course a bit artificial. Okay. And just to finish, let me make the last point. Be careful. Yeah. AC spectrum. No, better say pure point. As I said, pure point spectrum can be dense. For example, take here the measure that has atoms in all rational points. This measure exists. Therefore, so excuse me, please. I am in hurry that I do mistakes. This is too fast. Let me introduce two more notions. And this will be at the end of the classification. There is one more classification. So we now introduce the classification. There are types of the spectrum. The spectrum could be absolutely continuous, singular continuous, or pure point. All, of course, it could be a mixture. In particular, we believe that in three-dimensional Schrödinger operator, near the spectrum edges, there will be pure point, but in the middle of the band of the spectrum, there will be absolutely continuous spectrum, but it is still an open question, at least from the point of view of mathematical physics and spectral theory. While in one-dimensional case, the spectrum of random Schrödinger operator is pure point, and this I am going to prove you, I hope. And we will play a lot with this, but just to finish, I would like to introduce one more notion. The first is discrete spectrum. This is a set of points of eigenvalues of A, the atoms of resolution of identity of finite multiplicity and isolated. So discrete spectrum, I repeat, these are isolated points. That means if a point of the spectrum is belong to the discrete spectrum, there is a small, maybe a very small neighborhood, but such that there is no eigenvalues, the points of the spectrum inside. And each of them has a finite multiplicity. You remember, what is the multiplicity? It's from finite dimensional theory. How many eigenfunctions corresponding to this eigenvector you have? If the finite number, you say that the finite multiplicity. In finite dimensional case, of course, multiplicity is always finite, but in infinite dimensional case, it could be infinite in principle, yeah? So it is discrete spectrum, and the notation is and then you take another part of the spectrum, which is called essential spectrum. So it is just the rest. So these are not isolated points, and maybe isolated points, but infinite in multiplicity. It's quite possible. So this is another classification different from that one, in a way more rough. This classification is known since beginning of 20th century. In fact, in essence, it belongs to the great mathematician 20th century Hermann Weyl. While this classification was given in 50s by Toshio Kato Japanese mathematician. Despite that, people already knew a lot, of course, at that moment that there are different types of the spectrum, from the scattering theory, from many things, but just abstract definition, which is quite useful to now to be, belongs to the Toshio Kato. And we have another classification, I repeat, essential and this and the spectrum. And now, in third point, it's called sigma epsilon, just is the set of all eigenvalues. So a bit different from that, yeah? What is the difference? The points of sigma epsilon not necessarily isolated and not necessarily of finite multiplicity, but still the eigenvalues. What does it mean? The set of atoms of resolution of identity. And of course, I can relate this notion to the one of those, because if I take the closure, I will get pure point spectrum. Because I repeat, the spectrum, in the sense of in the sense here, it's always a closed set. Because how did I define? I defined the components of the spectrum via the spectrum of certain operator. Therefore, by general theory, the components of the spectrum are always closed sets, while the eigenvalue is not necessarily closed. As I said, the set of eigenvalues could be all rational numbers from the interval 0, 1, and then the sigma pp will be just 0, 1. And it happens in Anderson localization. Okay, now we have this complete classification, which is, I think, the last item of the abstract spectral series that I need to use now. We have 15 minutes for questions, but if there are no questions, I will continue.
Just to understand better, what is the relation between this classification and
Not too much, okay. Just okay.
just two different types.
Two different types of classification. You know, no, in fact, no. But I think you feel intuitively this classification is more rough.
Yes.
It's simpler. Okay, the precision is much less of this, but this is quite refined classification. You know, and I repeat, before the random Schrödinger operator, spectral theory dealt mostly with the first and third. For example, if you take the Schrödinger operator with fast decaying potential, which is called scattering theory, it is known that the spectrum consists of semi-axis and and maybe infinite number of eigenvalues with the unique accumulation point and 0. The standard spectrum, for example, I take Schrödinger operator continuous. The potential, for example, Vx decay faster than the dimension of the space. I take in d-dimensional space, R3 for example, I take the potential which is bounded and decays fast enough at infinity, then it could be proven that the spectrum of this operator is sigma AC coinciding with 0 infinity and plus sigma pp, which is just, so it is the absolutely continuous part, and you have eigenvalues here that could or could not accumulate, but if they accumulate, but only to 0 point. The last thing happens if you take maybe most important potential, it is just the Coulomb potential. In this case, you have infinite number of eigenvalues that accumulate to 0. And you have absolutely continuous spectrum, scattering states in quantum mechanics, positive energies. In all this scattering theory, it's a very important part of both of mathematical physics and quantum mechanics. And people spent a lot of efforts to prove that this strange thing will not appear there. And the main theoretical mathematical efforts were to prove that this is absent. Okay, so we finished with the general spectral theory. Now I would like to start to say a bit about most important so far operators. In fact, about two classes of operators from which general spectral theory grew up. Because everything was modeled, in fact, from differential finite difference operators known since the beginning of 19th century. Yes?
Maybe you should have mentioned from the very beginning that we are only working with densely defined operators.
Sorry?
Maybe you should have mentioned from the very beginning that we are only working with densely defined operators.
In fact, I mentioned, maybe not too explicitly, that we are going to work in essence with bounded operators. I don't want to bother neither me nor you with a lot of intricacies related to unbounded operators. And I said that this is why I'm like this. Because in random Schrödinger, roughly speaking, potential is bounded. It could be unbounded, but it is not too serious unbounded. So I'll mention this notion a bit later. This point, since you're asking, I mentioned this is a bit later, but maybe you remember I showed the two phenomena that we have. We have the phenomenon that operator could be unbounded, and second, the spectrum could be not just operator multiplication on 0, 1. The spectrum is not necessarily isolated points. I said we will be mostly concerned with the second phenomenon.
Yes, I mean,
More question?
but if you define a joint, then you need this condition necessarily.
My God, I said this is just to be, okay, minimally complete. Don't ask me in 5 lectures, give you all the spectral theory, which is thick book, you know. You can ask any question, I'm ready to answer.
And the fact that the kinetic part of a random Schrödinger p squared over 2m, the Laplacian, is not bounded, doesn't play a role. He keeps emphasizing that the bounded operators have everything in random
Yeah.
Schrödinger.
Yeah,
And
let
you
me
were saying
answer.
that the potential is
You
bounded.
know,
but
the
kinetic energy
the
is
things and the difficulties that we have in random Schrödinger operators, they are not related to unboundedness operators. They are in a different part of the spectral theory. And because of that, almost all people work with discrete Schrödinger operator. And you do not bother yourself with unbounded domain of definition because it is a common attitude, a bit even unconscious. You know, we did not do it specially. We found that the most important and interesting things that you see already for bounded operators. Suffice to say that, for example, to prove that the spectrum that you have Anderson localization for one-dimensional discrete Schrödinger whose potential is 0, 1 Bernoulli is just 10 years old. It's quite a hard problem, nothing to do with unbounded operators. So it is a kind of unconscious, trend of the theory that we found that most important things you see already for bounded operators. So why to do your life is even more complicated with that. This is no, but of course there are problems, but they are not too important. And even if you have unbounded operators, since we are discussing that, maybe I have to make 2 points. Unbounded. Just a remark. Unbounded operators. And there is a theorem which, in fact, I'll mention 2 results. The first is very simple. If A is self-adjoint, I don't know why, but I know that it is self-adjoint, and B is bounded self-adjoint, then A plus B is self-adjoint. So people used to say that the property to be self-adjoint is stable with respect to bounded perturbations. And this covers immediately all discrete Schrödinger operators. For example, take Schrödinger discrete operator plus Gaussian potential. It is not bounded, but it is diagonal operator. Any diagonal operator is self-adjoint. Plus discrete Laplacian, which is bounded. You are done. And the second thing, okay, which covers quantum mechanics, because in quantum mechanics, operator could be potential could be also quite, there would be Coulomb. But there is a theorem, it is simple things. So if you have continuous Schrödinger, then it is self-adjoint if V so your function is bounded. You can no, it's bad written. Excuse me. No. Excuse me. Better to write in this way. Where VR is bounded. This is just bounded functions, L infinity functions, yeah? And V2 is square integrable. So it covers practically all quantum mechanics, many body problems, scattering problems, Coulomb, etc. Because Coulomb, you can just isolate this singularity, it is square integral. This is famous Katov criterion. And in the notes that I use, there is a reference on the book, on the chapter of the book by Katov. There is a book by Katov, Perturbation Theory of linear operators, in which it is proven. And the third thing, 1D, for example, continuous Schrödinger, just minus d over dx plus v. To have this operator not self-adjoint, you have to assume that your potential faster than minus x squared. So it is minorized by minus x squared. It goes quite fast to minus infinity. And the physical reason for Schrödinger operator to be non-self-adjoint is very transparent. Because if you take corresponding classical problem, you have a particle moving in a given potential. For the Schrödinger operator to be not self-adjoint, you have to have the classical dynamics roughly, more or less the same. You have to have attracting center at infinity. The time to go from 0 to infinity should be finite. So it's a kind of, if you have a particle coming to the center of the you know, in quantum mechanics, there are examples when, if you have an attraction center, the potential minus 1 over R4, for example. So if your classical dynamics is such that classical particle goes from 0 to infinity for infinite time, your quantum problem is well defined, it's self-adjoint. So there is there are things, for example, if in accelerators, they made these so-called magnetic traps, which is these very good examples of not self-adjoint operator, with self-adjoint extension, etc., etc. So there are things in physics when you need, but not too much. Okay, so now I think I can finish. I'll start the next part.
All right, so we're having a break for tea, and please reconvene at 4 o'clock for the first research seminar. This will be by Benjamin from Leeds.
This was